Hello everyone, welcome to what will be our pre-lecture for lecture number 2. We're going to talk about equilibrium. So for the most part in Gen Chem 1, every chemical reaction that we talked about had a reaction arrow that went from left to right, basically between our reactants and our products, right? We would consider these to be irreversible reactions, and that means that they only go one way. However, in reality, there are actually quite a few chemical reactions that are reversible, meaning that they can actually go both directions. Our reactants are still going to be on the left, our products are still going to be on the right, but we would say that these reactants and products are in equilibrium. And so we use this two-headed arrow, basically meaning we have this equilibrium between our reactants and our products. So the relative concentration between our reactants and our products may vary greatly. We'll talk about how we calculate that a little bit. But it doesn't matter how much of the reactants or products we have, just that we have both that are present. Okay? Later in the semester, we're going to talk about chemical kinetics. That will tell us how fast a reaction goes. But with equilibrium, I want you to know that it tells us how much products we will get, or how many products we will get. We often actually end up expressing equilibrium as a ratio between our products and our reactants, and we call this equilibrium dynamic. So what dynamic means in equilibrium is that the rate of our forward reaction and the rate of our backward reaction are going to be equal. So once we reach that dynamic equilibrium, the quantity of our products, the amount of our products and the amount of reactants will not change as long as we don't have a change in temperature, pressure, or the addition of more chemicals. So if we look at these two charts here, for this first one, we have concentration on our y-axis. So we see we have changes in concentrations between our reactants and our products until we reach equilibrium. Once we reach that equilibrium, our reactants and our products don't have the same quantity, but they don't have a change in quantity. Okay? We can contrast that with when we have the rate of a chemical reaction. We can figure out the rate, and those will end up being equal for the forward and the reverse reaction once our equilibrium is reached. Okay? And so this is something we've actually seen before, and when we talk about equilibrium, that can also exist between phases. So if you think about our vapor pressure that we talked about in Chem 121, we can have an equilibrium between a liquid and a gas going between the two. And so an example of that is bromine, shown right here. The element bromine exists mostly as a liquid, but there is an equilibrium in a sealed container between it being a liquid and a gas. Okay? So how do we do math with relation to equilibrium? Oftentimes we calculate what's called the reaction quotient. And so this is derived from the stoichiometry of an irreversible reaction. And our mantra for basically the first month of Chem 122 here is going to be products over reactants raised to their stoichiometric power. So Q is just the concentration of our products multiplied by each other. Each of those products has an exponent that is the stoichiometric coefficient, shown by the lowercase letter here. And our numerator is going to be products. Our denominator is going to be reactants. Okay? We can also express this, so these brackets, I should say, are shorthand for concentration. We can also express equilibrium in terms of partial pressures, again, taking stoichiometry into account. One thing with the partial pressures, you want to make sure you are in atmospheres ATM in order to calculate Q. Okay? Q has a value that is unitless. The reason that is beyond the scope of this class, but if you take some upper division chemistry, you'll talk about this. Key takeaway there is that any value for Q doesn't actually have any units, so it's just a number. Finally, the numerical value for Q, the actual number we get, describes the ratio between our products and reactants at any point before our equilibrium is reached. Okay? Once our equilibrium is reached, again, we'll no longer have changes in our concentrations of our reactants and our products. So say for this reaction, when we first start it, our products are going to have an approximate concentration of 0 if we're just starting with reactants, so Q will start out being very small. Say we were looking at the reverse reaction, and our concentration of reactants would be about 0, and so Q would end up being close to infinity, or at least a very large number, right? And so once a system reaches that dynamic equilibrium, we call it K. And so something to basically important take-home point here is that K and Q are calculated the same exact way, and they're going to be equal at equilibrium. And so K is just Q, but when we are at equilibrium, Q is also equal to K at any point we are not at equilibrium. Okay? So we can express these chemical reactions in terms of basically the reaction quotient or the equilibrium constant, K. When things are in the same phase, that's pretty easy. We just take our products over our reactants, raise it to whatever power our stoichiometric coefficients are. So because we don't have any exponents here, that just has an implied value of 1, right? Another example, if we were to do that for gases, so you'll notice all of these are gases here, we could write this as Kp, where we have this should be Kc, where we have concentration, so we could report it in concentration. We could also report it as Kp, which is our partial pressure equilibrium, and so this would be the partial pressure of ammonia squared over partial pressure of N2 times partial pressure of H2 to the third, okay? And we can convert between Kc and Kq. Basically, the thing to know here is R and T, our good old ideal gas constant, and the temperature in Kelvin from our first unit, and that is going to be to the power of the change in the number of moles. And so, for example, we have 4 moles of gas in our reactants on here. We have 2 moles on our product side, so delta N here would be 2 if we were converting between Kp and Kc. Okay? We also have heterogeneous equilibrium, and so a key thing to note here is that pure liquids, anything with the phase designation L, or solids, phase designation S, are not counted as a part of equilibrium. That's for reasons that are beyond the scope of this class, but if you take upper division chemistry, we can talk about it at that point. However, I want you to do some practice before class ideally. Write out what you think the heterogeneous equilibrium expressions are for these reactions here. So basically, K is equal to something, products over reactants raised to their power, but again, taking into account that we don't need to count liquids or solids. So that's some practice you can do before class. Okay? And that's it for the pre-lecture. If you have any questions, please let me know. Otherwise, I will see you in class.